All right, let's try another one here from our fluid dynamics, and things are bouncing around. And so this is a diffusion one. And so remember that if you have, either air or water molecules floating around, and you have some different molecule, maybe this one here, it'll bounce around, ding, 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 and it will make slow progress. Even though it's moving very fast, it will then diffuse very slowly. And without proof, your authors said that the distance it would travel would be the square root of 2 times some factor that we refer to it has its diffusion constant here. Okay, and so it's like, okay, what is its value here, and then multiplied by time. And in our case, our diffusion constants, we're gonna look this up. But the problem here says that oxygen reaches the veinless cornea of the eyes by diffusion through the tear layer. And I always find this interesting that your eyes, the cornea, gets its oxygen supply by diffusion. There is no blood vessels supplying the oxygen, and that's kind of interesting. I guess it's really no different than salamanders, or a lot of your wet reptiles here. Maybe reptiles is the wrong word. Are they amphibious? Amphibians. Anyways, but they grab the oxygen and it soaks in or diffuses through the skin. Doesn't do it very fast, and so it can't go very far, and that's why it's important that these animals be small in size. They just couldn't get the oxygen, and so us humans, we couldn't get enough oxygen. We're just too big to get oxygen that way, so we have a circulatorial system. And anyways, but you guys, I'm sure, understand that whole life science far better than I do. So what's going to happen here is says in 65, it says 64. It says oxygen reaches the veinless cornea of the eyes by diffusing through its tear layer, which is about 0.5 millimeter thick. How long does it take for the average molecule to do this? So they're asking us to solve for time, how long. So I'm going to take x and then square it, and that'll give a 2dt, and then I'll get t by itself by saying it's the distance squared over twice the diffusion constant. So we are traveling a thickness of 0.5 millimeter. So let me put 0.500 and then millimeters and square it. And so I'm kind of thinking we're going to want units of meters. So I've changed millimeters into meters. So there's 0.5 millimeter. It really depends what the constants are, or the units for the constants are. Let me grab the book again. But looks like the diffused molecule is oxygen. Oxygen in water has a 1 times 10 to the minus 9. And there's the unit in meters squared per second. Okay, so 1 times 10 to the minus 9. So 1.0 times 10 to the minus 9. And remember, it was meters squared per second, which is actually a great set of units. And so my hunch was right. That's probably going to be in meters. So I got meters squared over meters squared. And then the seconds in the denominator flip and multiply. And we're going to get time in units of seconds. Good. And so let's run through the math. So 1/2 times 10 to the negative 3 squared in the numerator, divided by a 2, also divided by 1 times 10 to the negative 9. And so this is about 125 seconds. And I guess I might ask about significant figures. I think I had two. So if we wanted to call it 130 seconds, that would probably be better. Anyways, and so there's the time. All right, nothing fancy there. We never derived this, but hopefully conceptually you understand it, even though we didn't derive it, and you can at least use it. So now it becomes more of a plug and chug little formula. All right, so hope that helps you also with your fluid dynamics and your appreciation of physics and as it is applied to the life science. All right, take care.